So I want to conclude now with let's recall the statement at this point. So we had our theorem was that if f is C2 2 pi periodic, then these together imply that f theta is the sum from minus infinity to infinity an e to the in theta, where an is equal to f hat n, which was defined as one of the inner product. Let's write things just using that with en, and where the convergence is uniform. Okay, so let's conclude how this all fit, how the pieces come into play. Well, by 3 above, we know that the coefficients an decay like c over n squared when n is not equal to 0. By 2, we know then that the series converges uniformly to something. By a calculation above, we know that g hat n is equal to f hat n for all n. And then by the uniqueness, g is equal to f. So we get that f theta is equal to sum minus infinity to infinity an e to the in theta. So all these pieces fit together into this puzzle of proving this theorem. So there's convergence condition that comes from Weierstrass-M test. There is the condition that allows us to get that. So this is here. There's the condition that gives us that convergence condition. And then there's the uniqueness that guarantees that these two things give us the same answer. Okay. Any questions? So before I do an example, I want to say that it's true that Fourier series converge in much higher generality than what I've said. You don't need to be C2. I said already one weakening that really you need only a bounded second derivative. And it doesn't even have to quite exist everywhere. It can have some exceptional points where it doesn't exist. But there are a lot of theorems about convergence of Fourier series. There's a full, you could spend semesters long studying this topic. So this is not the end all. This is just to give a sense that you have one theorem that at least gives you convergence. So it holds much more generally, like almost any reasonable function has a convergence Fourier series. So the issue is just how it converges. Like, usually it's not uniform. Like for piecewise functions, piecewise continuous functions, you do still have a lot of convergence, but you will have some jumps, and you don't hope for uniform convergence. Well, for someone, yeah. Okay, so I want to do an example of this, also to bring in some of the integration by parts tools, and this is related to the whole one of the homework question that you have. So there, I posted it on Campus Wire. There is an assignment due this Saturday at noon, and at Pacific Standard Time. It looks long, but trust me, each piece is really, it's just mainly coding a theorem, and it's asking you to put these things together in a nice way and do some small calculations. So let's define a function, theta minus pi squared, if theta is between 0 and 2 pi, and then extended by periodicity. So I define it for other values by shifting this thing and adding it back. So the graph will look like these from R to R. Okay, and you'll observe immediately that not even C1, technically speaking, because there's that jump point there. So as said, why I do this is that actually for the C2 theorem that I stated, it's not, you don't have very nice examples. So I'll take a little bit of a liberty and we will pretend that the Fourier series converge for this. Actually, the proof that you'll do in the homework, that could be used to prove that you actually converge to the function f by following this same scheme. You compute the Fourier coefficients, you show that it converges to something uniformly, and then you argue that those two things have the same Fourier coefficients. And then again, by uniqueness, they must be the same thing. So there is a proof along those lines. But I want to just say something about just how this connects to something interesting and to show some of these tools. So, okay, we have this function. How do you find the Fourier coefficients? Well, the Fourier coefficients are computed by the inner product between the function and the basis element, and there's the conjugation, so that gives you the minus in theta. So you get this expression. Now there's always two cases. N equals 0, that needs to be treated separately. But n equals 0 gives you that this part here is equal to 1. E to the 0 is still equal to 1, even for this complex thing. Or if you have cosine n times 0 plus sine n times 0 I, well, this imaginary part vanishes and the real part becomes 1. So the formula also agrees with this. So this gives us 1. And then this is just an integral of a second order polynomial. Trust that you can all do this with the substitution. You get pi squared over 3, assuming that I did this right. Okay, so what about the other coefficients? Well, this brings us back actually to how do you prove these bounds on the coefficients? Whenever you have something times an exponential or something times a trigonometric, ever since calculus, you have seen that integration by parts is a nice tool. And that is actually one of the main tools that you use in Fourier series. You'll see the Friday video that also uses this. But okay, so if you want to find this integral when n is not equal to 0, well, what you can do is you want to decrease this power until it gets to 0. Now you do that by integrating by parts. So your f is this function. This is what you differentiate. And this is what you integrate. Now, when you, okay, so what you will get, there's one of the terms will be minus integral of the derivative of this function. The derivative of that function, I missed a 2, I think I missed a 2 there, is 2 theta minus pi. And then the integral of this function would be e to the in theta divided by in. And this is the source why this is such a powerful technique in Fourier series, is that you get these 1 over n's that pop out. Okay, you get the r units, so you have to imaginary units, so you have to be very careful about the signs. But then you play this game again. You take this as your function f, and this as your function g prime. So second round, second integration by parts. And something I didn't highlight with the first line is that you have a boundary term here. Now, so you get 2 terms. You get one of them is an integral where you differentiate this again. Okay, you should have well, the 2 I pulled out. The 2 I pulled out here. So you have e to the minus in theta over in, the integral function of this again. And I also pulled the minus in factor out here. And there's the minus sign. I may have made a sign error, but I think this is right. It's hard to keep track with these, but okay, so something about both of these terms. this term here is an integral of I e to the in theta. That's always equal to 0. I mean, you can just integrate it now. So you pull out a 1 over in theta, you substitute 2 pi and 0. Both of those by 2 pi periodicity give you 0. What about this term here? So if I was careful in this first integration by parts, there should be a boundary term here as well. There should be a substitution from 0 to 1 of f times g, or substitution from 0 to 2 pi of f times g. But f is 2 pi periodic. G is a complex exponential, is also 2 pi periodic. So what do we get? We get f g at 2 pi minus f g at 0. But these are equal, so it's equal to 0. So usually the boundary terms, if you set things up nicely, vanish. And that's what happens in the first integration by parts. But when you get to the second iteration by parts, you don't get 0. So you have to write out the substitution carefully as this expression here, and then you can substitute in it. So let's do this now, see what we get. So first of all, I want to factor out minus I times I is 1. So I have 2, and 2 over 2 is 1. So I'm left with 1 over pi n squared. And then I have a substitution from 0 to 2 pi. So let's see what I get from the numerator when I plug in 2 pi. And this is almost over. So pi e to the minus I n theta, that will give me e to the minus I n pi, and then minus pi. And this gives me minus 1 to the n, after some thought. So this will give me 1 over pi n squared when n is even, and 0 when n is odd. The Fourier coefficients look like that. But the main thing is the coefficients decay like 1 over n squared. So the Fourier series converges uniformly. It converges to some function. And because g hat equals f hat, and g and f are continuous, and 2 pi periodic, then f is equal to g. So we get that the function, by this argument that we presented above, is the sum of its Fourier series. And let's write out the Fourier series a little bit nicer now. So pi cubed over 3 plus sum over n even, and I'll sum it over equals 2k when k goes to minus infinity to infinity. And what we get here, so the pi's cancel, so 1 over n squared. This is the miracle that happens. So we get a sum over 1 over 2k squared e to the I 2n k 2k theta. But here you start seeing things like sum over y over k squared when k goes to 1 to infinity. So this starts being very interesting because you can then use it to compute things like 1 over k squared. So this is something you will work through in your homework. And but this example shows how you compute these using integration by parts, and how even without those assumptions, sometimes you will be able to get the convergence and you can get this machine to work. So thanks for your attention. On Wednesday and Friday, we will just talk about differentiability.